Welcome to Operating Systems Unit 9, Part 3. Here's some more on process synchronization. In this video, we're going to talk about monitors, which is another software solution to the critical section problem, and review some classic problems of synchronization. So let's get started with monitors. A monitor is a way to encapsulate the critical section by making a class around the critical section and then allowing only one process to be active in that class at one time. So instead of having each process have its own area in its code where it's manipulating a global variable, what you do here is you take the critical data itself and you put a class around it. And the usual setup is to have a we're going to use the keyword monitor. Of course, that's language specific. But the usual way to set it up would be to have the name of the monitor and some initialization code and procedure to request the critical data and a procedure to release the critical data. So this is very language dependent. So as for this class, we're just going to discuss it as a concept and an idea, and we'll do some examples. So let's get in here and get a schematic view of this. So basically what happens is you have the shared data, the critical data that's shared, and you can perform operations on that critical data like request it, release it, and maybe you have some helper functions. And then you have a queue of processes, and you cannot allow a process to request and release at the same time. If a process is making a request and checking to see if the critical data is available, all other processes must be blocked out. The only way that a process is active in the monitor is only one at a time. And the only way for a process to become inactive in the monitor is to either be using the critical data or using the resource, waiting on a condition variable for that resource, or finished with the resource. So there are condition variables. So again, a process becomes inactive in a monitor when that process is either using the resource because it went in there, did the instructions to run the request, was able to get the resource, is actively using the resource, and then it's not actively running monitor code. Or it is waiting on a condition because it got in there, made the request, but the request could not be granted, or it's finished with the critical data and it's no longer active. So here is a view with the condition variables. Same idea, you just could have different conditions to that the processes would have to wait on. Obviously, if you go in there and you run the request, but the critical data is not available, you don't want to have to start back again to run the request. There could be a line in the code where you've already checked a few things out, and then you could be next in line to access the critical. So now we're going to start to talk about some classic problems of synchronization that are used to test these synchronization schemes. The first one I'm going to talk about is the dining philosophers problem. So the dining philosophers are these 5 philosophers that spend their lives either thinking or eating, and they sit around a table, and as they sit around the table, they either they think, which is they just are just sitting there, or they eat. And if they want to eat, they need to pick up 2 chopsticks in order to eat. And yes, they're sharing chopsticks. That's the point, is that they have to share chopsticks. And if a philosopher decides that they want to eat, they need to pick up each chopstick one by one and then eat. And then when they're done eating, they put their chopsticks down one by one. So in the case of the 5 philosophers, the shared data is there's a bowl of rice. That's what they want to get to. And the way that they get to it is by the chopsticks. So if you were doing the semaphore solution, you would initialize each chopstick to 1. And the philosopher would say, oh, you know what? I want to eat now. So I'm going to check my right chopstick and see and run my weight. And if it's a 1, if you remember from the last video, a 1 means that I can pick up my chopstick, so I'm going to pick it up and then change the value to a 0, in which case the other philosopher, if they wanted to pick that up, they can't because I'm using it. And then I'm going to have to check my other chopstick. So each philosopher in the semaphore solution to the dining philosopher's problem must pick up both chopsticks in order to get into that critical rice and start eating the rice. So here's a semaphore solution for the dining philosopher. So for example, if the philosopher goes to pick up one chopstick and then it's mod 5, so it picks up the other chopstick. So it runs its weight on the one chopstick and then as it runs its weight on the other chopstick, then it picks up both of those chopsticks, eats the rice, and then signals the one chopstick and signals the other chopstick. And so there is a problem with this algorithm, which we will discuss in just a moment. But first, since we're talking about monitors, let's take a quick look at the monitor solution to the dining philosopher's problem. The dining philosophers in the monitor solution here, if you take a look, instead of, you have the monitor key name. The name of the monitor is dining philosophers. It has instead of a request, it has a pickup. Instead of a release, it has a put down. It has initialization code where it initializes all of the philosophers to the state of thinking. The philosophers can have 3 states: thinking, hungry, and eating. And when a philosopher decides that the philosopher is hungry, then that philosopher will change its state to hungry, run the pickup, and in the pickup it will then test to see if it's able to pick up both chopsticks, and if it's able to pick up both chopsticks, it will eat. If it's not able to pick up both chopsticks, it will go into a wait condition. If you take a look at the pickup, it says if it is not eating, it will be in a wait condition. Now, the thing about this is that in the put down, when a philosopher goes to put down, means it changes and decides it doesn't want to eat anymore. It's going to test its neighbors to see if its neighbors are waiting. So in this situation, in this monitor solution, the one who puts down the chopsticks will then signal to the ones who are waiting that they can then come and pick up the chopstick that they were waiting for. So this monitor solution does not, it solves the problem without causing any kind of deadlock, and it's a good, fairly easy to understand, if you understand the dining philosophers, a fairly easy to understand monitor and the concept of a monitor. So take a look at it. Take a look at the way it's set up. It has the keyword monitor, and then it has a request or a pickup, a release or a put down, and it has another helper function, which that's perfectly fine in a monitor. You can have as many functions as you want. And it has initialization code. So this is one of the monitor examples, and there are other monitor examples on Blackboard. So here's the problem with the semaphore solution to the dining philosopher's problem. In the semaphore solution to the dining philosopher's problem, you have your 5 philosophers and you have your 5 chopsticks. But you may end up in a situation where each one of your philosophers has picked up only one of their chopsticks. And this is going to be a lead-in when we get into deadlocks, because this is right here, we are stuck in a deadlock situation. Now the semaphore solution can eventually, if the philosophers are consistently picking up, say, the left chopstick and then the right chopstick and then putting down the left and the right, if there gets to a point where all of them have picked up their left chopstick, then you could have a deadlock situation. In the monitor, because only one philosopher can actually be active in the monitor at a time, then it wouldn't be possible for a philosopher to only pick up one of its chopsticks, because it cannot change its state to eating unless it picks up both. There are other classic problems of synchronization that I've outlined on Blackboard. The bounded buffer problem that has a semaphore solution, readers and writers that are, and on the Blackboard too. There's first readers and first writers, so please take a look at those and email me if you have any questions. Thank you.